Here's an example of using a Taylor series to figure out something completely new and different. So let's ask a question that seems a little crazy at first. What is e to the I? Now, this is sort of a weird question because this exponent is imaginary. And what does that even mean? I mean, our definition for exponents really only makes sense for real numbers. So to answer the question, what is e to the I, it's really a question of what should this mean, and not so much a question of what is it, because it doesn't mean anything until we've actually defined it. So what could it possibly mean? Well, if you think about e to the x, what we're really doing is we're just putting an imaginary number in here instead of x. So maybe what we should do is think about the function e to the x. And as we now know, e to the x is the same as its Taylor series, which is the sum from k equals 0 to infinity of 1 over k factorial times x to the k. And we know this converges for all values of k. So it should converge for even if we put imaginary numbers in here. In fact, it does converge if you put imaginary numbers in here. You have to be a little careful about the magnitudes of imaginary numbers, but it turns out there's no problem. So let me write out the first several terms of this series just so we can see them. So the k equals 0 term is 1. And the k equals 1 term is 1 times x to the first. And the k equals 2 term is 1/2 times x squared plus 1 over 3 factorial x to the third plus 1 over 4 factorial x to the fourth, and so on. This keeps going forever. 1 over 5 factorial x to the fifth plus ... Okay. So what we're going to do to try to make sense of what happens for imaginary powers is we're just going to replace x with x times I. Actually, let me use a theta instead of an x. Okay, when we do that, the left-hand side turns into e to the theta I. And the right-hand side, well, let's just plug it all in. We get 1 plus theta I plus 1/2 times theta I squared plus 1 over 3 factorial times theta I to the third plus, and so on. I'm going to stop there. And then, having these i's with exponents, that seems like something we could simplify because we know what the powers of I are. So this is 1 plus theta I plus 1/2 theta squared times I squared. But I squared is -1, so that's going to make this plus a minus. Okay, plus 1 over 3 factorial times theta cubed times I cubed. But I cubed is negative I, so that makes this plus a minus, and that gives us an I right here. Okay, plus 1 over 4 factorial times theta to the fourth times I to the fourth, but I to the fourth is 1, plus 1 over 5 factorial times theta to the fifth times I to the fifth, but I to the fifth is just I, and then so on. There are some more terms, but the pattern of signs and i's just repeats. We have a positive I, a negative I, a positive I, a negative I, and so on. Okay, so what is this big mess we've made for ourselves? It's a little hard to see, But let's separate all the terms that have an I from those that don't have an I. So the terms that do not have an I, I'm going to underline in blue. There's that one, the one term. There's the minus 1/2 theta squared term. There's the plus 1 over 4 factorial theta to the 4th term. So let's write those all down. I guess might as well write them in blue. 1 minus theta squared, 1/2 theta squared, plus 1 over 4 factorial theta to the 4th. The next one is going to be minus 1 over 6 factorial theta to the 6th, plus 1 over 8 factorial theta to the 8th, and so on. The next one is minus 1 over 10 factorial theta to the 10th, etc. Okay, and then plus, now let's gather up all the terms on the previous line that have an I. So that's the green ones here. And let's factor out that I at the very beginning. So I times theta minus 1 over 3 factorial theta cubed. And then the I, remember, we've already factored out the I from that term, plus 1 over 5 factorial theta to the 5th, and so on. The next term is minus 1 over 7 factorial theta to the 7th, and then plus 1 over 9 factorial theta to the 9th, etc. Okay. Now, everything in blue here, that might look familiar. If you think about it, that is exactly the Taylor series for a cosine of theta. Plus, and everything in green, well, there's the I, and then everything in green in these parentheses, that's the Taylor series for sine of theta. So e to the I theta is cosine theta plus I sine theta. So the reason that we've never been able to make sense of complex exponents before is because you get complex results. That's weird. So looking at this complex exponential, what this means is, let's just plot a few of these numbers. So when theta is 0, e to the I theta is cosine 0 plus I times sine 0. And cosine 0 is 1 and sine 0 is 0. So that point is right here. This is the point. This is just the number, real number 1. And this is e to the 0. It makes sense that e to the 0 is just the real number 1. Now let's see what happens when theta is pi over 2. We get e to the I pi over 2 is cosine pi over 2 plus I sine pi over 2. Cosine pi over 2 is 0 plus I times sine pi over 2 is 1. So this is all just I. And on the real number line, on the complex plane, the real number I is right there on the vertical axis. So that the imaginary number I is e to the I pi over 2. As the angle theta goes from 0 up to pi over 2, the complex numbers swing from 1 around the unit circle over 2I. And as theta increases more, they keep going around the unit circle in the complex plane. So raising e to imaginary powers just rotates you around this unit circle in the complex plane. One consequence of this is if you raise e to the power I pi, you get cosine pi plus I sine pi. So e to the I pi is cosine pi is minus 1 plus I times sine pi is 0. And then if you move 1 to the other side, you get e to the I pi plus 1 equals 0. And so here's an equation that has all of the important mathematical constants in it. There's 0, the additive identity, 1, the multiplicative identity. There's the exponential base, e, pi, and also the imaginary unit, I, all in one equation. This surprised, I think it was Euler who first discovered this formula. This surprised Euler quite a bit when he first found it. And I think probably since then, in the subsequent 300 years, every calculus student has learned this identity. So now you know too.